Okay, section 3.5, maximum minimum problems, and these are specifically going to be some business and economic applications. Now, there's only one thing in this section that we're doing, and you may have noticed it's a bit of a short section, and that's what we call optimization problems. Optimization problems. So anytime you see maximum minimum problems, maximize or minimize, you're optimizing. So the idea here is you're finding the absolute max or min for whatever quantity that you're measuring. And we have some strategies for maximum minimum problems or optimization problems. So the first thing you need to do, and you may laugh when you hear this, but it's read carefully. And draw a picture if you can. If you can. Now, some of you may think this is a silly thing to say is part of your first step, but I can't tell you how many times I've been helping a student or been working on a problem with a student, and I say, well, what did the problem say? And I'm not sure, I didn't read it that carefully. So make sure you're reading your problem very carefully. There is obviously going to be some extraneous information that gives you context for the problem, but almost all the time in these questions, if you're not using all of the mathematical information you're given, you've done it incorrectly. So that's why in step 2, what we want to do is list your variables. So we're listing out all known and unknown variables. With those, we need to make note of units. Note of units. And label the diagram that you made in part 1. So if you've drawn a picture, you've made a diagram, you're going to label that in step 2, and you know what all of your variables are because you've read carefully in step 1. So the next part, the next 2 steps are the hardest, and they're going to be where most of your work is going to take place. So we need to translate the problem into an equation to be optimized. And they're not going to say optimize, they're going to say maximize or minimize. And so one of the problems we're going to do is about profit and cost. Obviously, you want to maximize profit, but you would want to minimize cost. So you want to be on the lookout for those things and be thinking about what would you actually want in the real world. If you're building something, usually you want to minimize your material because that will minimize your cost, while maximizing your area or your volume or whatever, because that gives you the most use. So the next step and the last step is to rewrite your equation in one variable using a constraint This constraint has to be given to you. It's not something you're going to come up with. And then we use procedure from 2.4, 2.4, 3.4. So we're finding absolute maxes and absolute mins in this section, so that's why you use that. Okay, so we're going to walk through 3 typical examples, typical problems that you would see for optimization. So in this one we have a hobby store. It's got 20 feet of fencing to fence off a rectangular area for its electric train display, and it's in the corner of the room. And the 2 sides against the wall don't need any fencing. And we want to know what the dimensions of the rectangle will maximize the area and then what that maximum area is. So this is one of those cases where drawing a picture is very useful. So we know we have a rectangular setup, and we have a wall and a wall in one corner, and then we have these dimensions. And pretend I can draw a straight line here. So I'm just going to call this x and this y. So when I tackle these problems, what I always look for is, what is my constraint that I need to work off of, and what do I need to optimize? In this case, we're maximizing, and that's area. So the constraint given to us by the problem in this is the thing that limits us to what we can do, and the limiting factor is our 20 feet of fencing. So this is 20 feet of fencing. So then we have to think about, how does that relate to our variables? Well, that means that in total, x plus y can equal 20. That's all we have. That's the amount of fencing. And then when we come down to what we're optimizing, based on our diagram, we want to optimize or maximize area. The area of our rectangle is x times y. So now I have my equation. This is step 3. I've translated that equation into I've translated the problem into an equation. So now I'm going to come down here, and I'm going to combine area equals xy with my constraint that x plus y has to equal 20. So remember, step 4 is to rewrite our equation in one variable. So by substituting in, I have the area has to equal, I need to solve this equation for, I'm going to solve it for y equals 20 minus x. So our area has to equal x times 20 minus x. Now I have one variable, and we can start our procedure from 3.4. That means taking the derivative, finding the critical values, and determining what principle of the extreme value we're going to be using. So a prime, I'm going to rewrite this as 20x minus x squared. A prime is going to be 20 minus 2x. Set this equal to 0. And we get 20 equals 2x, or x equals 10. Now one thing we forgot to do, or we didn't forget, we need to account for, is this is feet. So x equals 10 feet. Now we need to check this. We have one critical value. There is a closed interval, 0 to 20. So there is some shortcuts we can take because this is a real world problem. So because we have one critical, we know we're going to want to do the second derivative. We're going to want to use principle 2 from the last section. So f double prime, we're doing a double prime. A double prime is going to be -2. That's going to be always less than 0. So a double prime of 10 is still -2, still less than 0. That means that x equals 10 feet is at max. Now normally when we had a closed interval, we said we needed to check our endpoints on that interval. In a real world problem like this, you don't always have to. So the reasoning here is if we think about, if we let x be 0, that means y is going to be 20. And then we don't have a rectangle anymore because we have no x. Same thing if we let x be 20, and this comes all the way out, y has to be 0 to fit our constraint. So we don't actually need to check our endpoints because those don't make realistic sense to actually make a rectangle. So we have x equals 10. Using principle 2, we know that that's going to be the maximum. So if x is 10, that means y's got to be 10 because x plus y has to equal 20. So these are our dimensions, half of our final answer. And then the max area is 10 times 10, or 100 feet squared. So those are the two parts to our answers. Okay, so if we continue on, flip the page, we have a slightly more difficult problem. And this requires more setup, so I've broken it into pieces to take us through. So we have a stereo manufacturer, and they want to sell X units, and they realize that to sell X units, their price in dollars needs to be modeled by this function. So it's based on the number of units they want to sell. And they also determine the cost of producing those stereos is given by this function, 3000 plus 20x. So I've just broken this into pieces. Now, in the homework, it's not going to give you these pieces. It's just going to give you this, and then your last question will be, what is the maximum profit? Or what price per unit must be charged? So I put these here to kind of give us a guide, so that when you're working on the homework or on the worksheet, you have a guide to these types of problems. So the first thing we want to find, revenue. Revenue, we know, is usually profit minus cost, but it's also price times units. So our price is 1000 minus x times x. So we have 1000x minus x squared. We have our revenue function. Our profit function now is cost minus revenue. I did that backwards. This is revenue minus cost. Revenue minus cost, 1000x minus x squared minus 3000 plus 20x. This is going to give us negative x squared. 1000x minus 20x is 980x minus 3000. And now here's the big question. How many units must the company produce and sell in order to maximize profit? So this is one question that could happen. Each of these C, D, and E are different questions, different types of optimization that you could be given. So how many units must you produce to find the maximum? Well, and we want maximum profit, so we need P prime. P prime is going to be negative 2x plus 980. Set that equal to 0. 2x equals 980. So x equals 490 units. We have one critical number. We know we have an open interval, and we know that because it doesn't give us a limit on x. So we know that we can sell no stereos all the way up to infinite stereos. So we know that we have this open interval. So that means we're going to want to do our principle 2, so finding second derivative. We're doing a second derivative test, essentially. So p double prime of x is negative 2. That's going to be less than 0 for all x values. Which means that x equals 490 units is the maximum. So that's going to give us our maximum. So now what is the maximum profit? P of 490 negative 490 quantity squared plus 980 times 490 minus 3,000. And I've just punched this into the calculator. And if you haven't already, I recommend you take a look at the link I sent you about getting a free TI emulator for 6 months, so you have a graphing calculator on your computer. And our max profit then is going to be $237,100. So that's our max profit. And then what price per unit should be charged or must be charged to actually make this? Well, then we go back to our price function. P of x, 1,000 minus x. So P of 490, 1,000 minus 490. And that equals $510. So let's say these are car stereos. This seems like a better price. So this is the price that you have to sell to make your maximum profit. Now, if you're looking to upgrade a stereo or buy a stereo, you might not want to spend this. So a lot of times as a business, you'll look at this number and you'll say, well, if I cut this by $60, will I sell more units? And the answer is yeah. Because if I make my price $60 less, so just on the side here, I'm saying my price is $450, which means that X is 1,000 minus $450, and X is going to be $550. Or I cut my price by $60. So I'm going to sell more units, which means I have more turnover, which means I have a better chance of restocking my store with other brands, other models, newer models, and you can sell things faster. So a lot of times, even they'll look at their maximum, and then they'll look at how fast they need to sell things, right? Turnover is very important as a vendor. So yes, you can make $237,000, but maybe making, whatever it would be if you plugged in 550, maybe making $200,000 is better in the long run because you'll have higher turnover, you'll get new stereos, you'll get more people in the store. Maybe they buy something else that's not just the stereo. So looking at maximum profit is very useful. Being able to know what your maximum profit is useful, but it's not the only thing that you look at as a business. Because assuming you're going to do this, if you set this price, doesn't mean that you're going to actually get there. Because yes, this price of $490 or this price of $510 may get you your maximum profit, but it also may not, because you're going to lose people. Some people aren't going to want to spend over $500. Sometimes they'll look at this and they'll say, well, let's just set it at $499.95. Gives people the illusion that they're spending less than $500, and you'll get pretty close to this value as well. So those are all things that companies consider when they're selling goods and services. Okay. So the last one here. This one is one of the more complicated problems we can see. So we have a retail appliance store. They're selling 2,500 TVs per year. Wait. That's not the same one I have. That's okay. So by keeping records, a theater determines that an admission price of $26 on average, it averages 1,000 people in attendance. For every drop in price of $1, it gains 50 customers. Each customer spends an average of $4 on concessions. What admission price should they charge? So this takes a couple things into account. Number one, we want to know the admission price going in. So right now, the average is 1,000 people. They want to maximize their revenue. For every drop in price of $1, it gains 50 customers. So the number of people, we'll call this P. This starts at 1,000, and then if you drop X dollars, what's going to happen? Well, you gain 50 people. So I think we need to use a different variable here. Let's call this attendance. Let's call this A of X. So you start at 1,000. For every X price drops, you're going to add 50 people. So X is number of price drops. And our price, so we're not going to call this, we're going to call this A. Our price, P of X, starts at $26, and then you subtract X price drops because it's in $1. So each customer spends an average of $4 on concessions. So we know that our profit, or our revenue, is a combination of the number of tickets they sell, and this is the price of the ticket, 26 minus X, and then times the number of people that are in there, 1,000 plus 50X, because this is the price per ticket, times the number of people entering. And each customer spends an average of $4 on concessions. So that's going to add an average of 4 times the number of people we get into the theater, 50X. So we can simplify this a little bit by factoring out the 1,000 plus 50X. And so we know that 30 minus X times 1,000 plus 50X will be our revenue. So this one's harder because we had to set up a couple things. We needed to know how many people, the attendance, which I called A of X. We needed to know the price of our ticket, which I called P of X. And we need to know our revenue is our number of units, our number of attendance, times our price, plus the average that they spend. So this is our average expenditure per person on concessions. So now we have a function, and we can maximize this function. It's already in one variable, so we're just going to do r prime of x equals derivative of the first, -1, times the second, plus 50x, plus the derivative of the second, which is 50, times 30 minus x. And then this equals what? This is going to be -50x minus 1,000 plus 1,500 minus 50x. So this equals -100x plus 500. And we're going to set this equal to 0. And x equals 100x equals 500 or x equals 5. So this is the number of price drops we should make. So again, we have one critical number. We know it's an open interval because we can sell, or we can make 0 price drops. Actually, we can make negative price drops, which would be price increases, or we can make as many price drops as we want. So we're going to do the second derivative, r double prime of x. We have this nice simplified version here, so I'm just going to use this as negative 100. And just as we saw before, this is going to be less than 0 for all x values. So x equals 5 is a max. So now, remember the original question is what price should the theater charge? So we know that the maximum profit, maximum revenue they can make happens when we decrease the price by 5 price drops. So our max, or our new price, will be 26 minus 5 $1 price drops, or $21. And that would be our final answer to this problem. So I do know some of these are easier than others, some of these problems. So for instance, this problem and this problem are harder. Now obviously I was going to have you do this in group work, so I recommend that you do try and set up some Zoom meetings with your classmates to try and work on these, and we can work on these together in office hours as well. But these are just 4 good, challenging practice problems that ask a lot out of you. If you can handle these 4 problems, the test questions will be easy comparatively. So I've picked these out specifically because they're the hardest of the hard. So that's the end of section 3.5.